Okay, our next speaker is Tobias Wenger. He works with us at JPL. Tobias works at this intersection of metasurface design and fabrication. As we just heard, design is important, of course, but critical is the ability to fabricate the devices that have been created. So, he focuses on wavefront sensing and spectropolarimetric metagratings. And let me just say that, I've looked to Tobias many times to create devices that I thought were challenging, only to have him come back and say it's done and it's operational. And I really value his contribution to our work. And it's really essential in translating these theoretical concepts into practical functional devices. So please join us, Tobias.
All right, testing. Can you hear me? Good, thank you. Thank you, Kent, for those kind words. Let me just tuck this away. So, I'm standing between you and lunch, and I apologize. I'll try to be as quick as I can. Let's see if this works. Okay. So the idea here is, so this is going to be a slightly different talk from the previous ones, where we talked about this when we set this short course up, and we thought that it would be interesting to have a talk where, assume that people don't know anything about microfabrication whatsoever. Looking at in the room, I'm not sure that applies to many of you, but so similar to Noah, I'm a little bit self-conscious. Maybe I took this to too low a level, but then bear with me. I hope it will get interesting. And if anything else fails, everything else fails, think about lunch. So what I will try to cover, let me see if I can. So essentially, a crash course in microfabrication, where I'll go over what I consider to be, or I think they are, the three main fundamental aspects of microfabrication, so patterning, lithography, depositing materials, and removal of materials, etching. What I will not be covering, but they might be, or they are almost as important, so surface preparation, surface cleaning, handling of your wafers, dicing, potential material interactions, et cetera, et cetera. So there are a lot of sort of detailed things that go into this, but fundamentally, you only need to kind of understand the three building blocks to sort of get the gist of microfabrication. And then, because it's a course, I'll apply what we learned into some examples of how to make these, at least some of these are what I consider to be pretty pictures. And I'll also try to, in the end, go into some of the challenges that I see arise in the sort of, if you take these beautiful designs that arise from some of these very fancy optimization technology or methods, some of the challenges that I see in how you actually translate that computer-generated design into sort of a real-world device that you can hold in your hand or put into a system. So some of those are sort of how do you select your materials, the resolution that you achieve and the aspect ratio that you hope to achieve, and I'll also address some other challenges depending on how much time I have left. So let's jump straight into it. Patterning, or micro or nano lithography. Essentially what we're talking about now is we're making or breaking bonds in a resist, and a resist is a liquid that's either photo or e-beam sensitive most of the time, and it's a liquid that you dispense onto your wafer, and then you spin your wafer really quickly, typically at a few thousand RPMs, and then the liquid, the resist, reaches a hydrostatic equilibrium on the surface, and that's a way to create highly, highly uniform coatings onto surfaces, onto a wafer. So it would look something like this. You have your substrate, you spin coat your resist, you expose it. Let me get back to what that means in just a second. You would put this into a developer, and if your exposed area is removed, that's called a positive tone photoresist, or resist, I should say. I try to avoid saying photoresist because e-beam, but I often slip and I say photoresist. I mean resist. You can also expose the resist, develop, and your exposed area remains. That's a negative tone resist. So this is kind of important to keep in mind when you're developing your process, because especially for e-beam lithography, sort of the right time can become an issue, so you want to not unnecessarily expose areas that you don't need to. So it's important to consider the tone of your process. Photolithography versus e-beam lithography. I think you can fill hours and hours of lectures talking about both of them and their comparative differences and similarities, and in which instance you might choose one over the other. I think it's generally fair to say that in principle, photolithography is sort of a faster process, and you're using photons to expose and to make or break the bonds. It's faster, but it doesn't really necessarily have the resolution that you get with E-beam lithography. So I think for most of the stuff that we're talking about here, E-beam lithography is sort of what we're talking about. And then one of the drawbacks with E-beam lithography is that it's an expensive sort of installation to run, and also it can be pretty time consuming because you're essentially writing you're not really exposing the full thing at once, you're kind of more writing the entirety of your metasurface. Okay, so now you know everything that you need to know about lithography. Deposition, so adding material onto your wafer, might be as simple as this. You have your wafer, you add, that looks like gold, so you add it just on the top of your wafer, you deposited it somehow. And it's an important thing that took me quite a while to get used to. So normally when you think of a material, let's say silicon dioxide, you think of silicon dioxide as this well-defined material that always has the same material parameters. That's not really the case. Depending on what methods you're using to deposit it, you typically get slightly different refractive index or density. So you always end up with some amount of impurities in there, and they sort of translate into the material properties that you end up with. So that's one aspect to kind of consider when you're choosing your method of deposition. Another thing to consider is that depending on the method you chose to deposit your material, you will also end up with, it matters then how your material goes down onto your surface. So in this case up here, I'm just putting this material on a blank wafer, so then it matters less. But conformality of the deposition process is something that's a pretty big deal. So what I mean here is that if you have a substrate material, blue here, and you have resist is always red in my pictures, and I deposit the material, if it's not very conformal, it's more like a line of sight deposition method. So notice here how this yellow material that I deposited, it doesn't coat the sides here. And on the other extreme, here, when it's very conformal, it will conform very well to the surface of or to your pattern itself. And even if you sort of consider having something that's tapered inwards here, you might even coat that inside. And why I'm making a big deal out of this is because this now has a lot of what you do subsequent to this deposited material and beyond in terms of your fabrication process. What you can and cannot do depends a lot on how you covered or not up the entirety of the photoresist. And I'll return to that in a little bit. So if I'm going to just list a few deposition methods. So evaporation is typically not very conformal. And then as we kind of move into the more conformal regime here, sputtering, chemical vapor deposition, atomic layer deposition is typically what's considered the most conformal method. So you can coat very nicely sidewalls. Okay, so etching. And I think this is quite a big topic as well on its own. Not that the others aren't. So essentially what we're talking about now is removing material somehow. And the first thing to know about this is that you have two fundamentally different types of etching, often referred to as wet etching or dry, or I'm going to call it plasma etching. So wet etching is you submerge your material or your wafer into a liquid, might be hydrochloric acid, hydrofluoric acid, etc. And you depend on the acid to do the work for you, and you don't have very many control parameters. You can dilute the acid, you can maybe heat it up, but that's about it. Whereas in contrast now, plasma etching, it's done in a special purpose tool where you put your wafer in, you pump a vacuum, you introduce gases very controllably, you strike a plasma, and you can bias the plasma, you can drive it at different frequencies, etc. So in modern etch tools, you can also decide which gases to flow into the system. So in modern etch tools, maybe you have even too many parameters that you can tune to get the etch performance that you want. Another thing that's going to be important when we talk about metasurface fabrication is isotropic versus anisotropic etching. So isotropic etching, so if you have a pattern, so you have a blue material that's patterned and you have a photoresist pattern on top, if you do an isotropic etching, typically you end up with something looking like that. That's often, at least for metasurfaces, not what you want. Typically, you would want to have very nice and vertical sidewalls, but the isotropic wet etch will kind of, while etching vertically, it will also etch laterally and kind of start undercutting your mask. And you can imagine if I have this in the etchant for too long, this whole feature is just going to disappear. In contrast, plasma etching can be highly anisotropic. So wet etching is typically isotropic. There are a few notable exceptions, but they're very specialized, so let's not go into them. Plasma etching can be very anisotropic. And I say can be because I think if you've worked for a little while with etching, you know that it's not always going to be the case. And this is it's highly material dependent, and you have to work often for quite a while to make sure that your etching is as anisotropic as you desire it to be. But in a perfect world, this is what you do. So you have your pattern and you perfectly transfer that in a completely perfect vertical anisotropic manner into the substrate or into the material below. The concept of selectivity is pretty important when we're talking about etching. And selectivity is essentially, it's a number, let's say 10, and it tells you how much faster you're etching, in this case, the blue material that you want to etch, than you're etching the red material that's working as your mask. So if I have a selectivity of 10, you etch the blue material 10 times faster than you're etching the red one. And it might seem like a minor detail, but this is very, very important because it tells you how thick. So if you know that your metasurface design calls for an etch, so a pillar height, an etch depth here of, let's say, 10 micron, if you have a selectivity of 10, you know that you need at least a micron of red masking material. And selectivities, they can range from, you can have selectivity that's lower than 1, meaning that you etch your mask much faster than you're etching your actual material. That's not the ideal case, but it does happen that you find yourself in a situation where you need to do that. But typically you have selectivities of maybe 50, 100, even several hundreds. I've even seen papers where they claim that they have 70,000 as a selectivity. So you then need almost no material at all to actually perform your etching. So that's an important consideration when you're sort of setting up the entirety of your process. Okay, so now you've taken the crash course. Now you know everything you need to know. To kind of follow along at least a few basic examples, I'm going to go through as many of them as I can. So is it true that I have 30 minutes left? 25, okay. Maybe okay. So the most straightforward thing to do is to make a pattern. So let's call it a metasurface, but it could go for any pattern. So you make a silicon metasurface using a photoresist mask, or maybe even an electron beam, sorry, a resist mask, I should say. So you start with your silicon substrate, you go out and you buy this. You've bought resist, or you find it in your clean room, you spin coat it on. So far everything is pretty easy. Now you have your computer generated pattern, you expose this pattern using your E-beam or your stepper system or whatever. You put it into the developer, you develop for as long as you need to make sure that you have your pattern. So now you have ended up with your metasurface pattern. It's just not in the substrate, in the material that you want, you have it in your resist. Now you take your favorite anisotropic etch that you magically found, and you do a perfect job of transferring this into the substrate below, so you create these well-defined vertically looking pillars, and then you remove your resist in the end, ideally without damaging any of the delicate features that you made. So it sounds pretty easy. So this is an example. So you can't see that therefore. So this is an example of how that might look like. So these are silicon pillars of varying sizes etched to, I think this is a depth of around 25 microns. And so I said that this is the most straightforward way of making a metasurface. And so that implies kind of there are less straightforward ways. But why would you do that? So this image kind of tells you why you would want to do that. You can see how you have some degree of ruggedness in the top of all these pillars. So that might not make a big difference depending on how tolerant your design is to these kind of things. But you can clearly see that at least these smaller pillars here, they're quite substantially, like their radius is diminished. So if you're not tolerant to that, you have to do something different, because this comes from the fact that your etch mask, your photoresist, has eroded while you did the etching. That's something that using photoresist is kind of hard to completely get rid of. You can try to mitigate it, but completely reducing it using photoresist is difficult. So one way to mitigate that is to use something that's called a hard mask. So in this case, I'm going to utilize a silicon nitride hard mask. So that's a pretty hard material, so it's not a photoresist. And I'm going to etch something into gallium antimonide, so which is a completely different method material from silicon, obviously. So you would start with your gallium antimonide substrate. You would deposit using your favorite method, silicon nitride. So here you're doing a sort of a blanket deposition, so it doesn't necessarily matter too much exactly what your method is, as long as you're getting a good material quality, as long as it's hard, is kind of what I mean. And then on top of that, you would spin coat your photoresist or E-beam resist. You would then expose it. We know this by now, right? So you develop it. Now you have your pattern in your resist. Now you use some kind of anisotropic etch. And let me pause here for 1 second. So every time I say etch now, one has to sort of consider what type of etch is appropriate to use for a certain material. So in this specific case, silicon nitride does not etch well in the etch that was used in the previous example with the silicon. So this is sort of a completely different, it's even in using a completely different tool from the tool that was used for the silicon etching. So using some kind of anisotropic etching, you transfer this pattern into the silicon nitride. Then to remove any kind of erosion effects, you would then remove your photoresist or E-beam resist. And now you use a third type of etch, because the types of etching that we did for the silicon and the silicon nitride does not work at all for gallium antimonide, which is a notoriously difficult material to etch. So you can then transfer the silicon nitride pattern into the gallium antimonide below. So you have gallium antimonide pillars. And then, if you're lucky, you remove the silicon nitride without damaging these delicate nanofeatures. So that might look like something like that. So you can clearly tell from this image, this is a very different type of sort of aspect ratio features than we saw for example, number 1. And this, at the heart of it, is because this material doesn't etch nearly as well as silicon. Okay, example 3. So now I'm going to use a different type of hard mask, aluminum oxide, which it's fairly popular these days to use because it's very, very durable, a very durable material that's fairly easy to still deposit. And so I'll return to this in a second, but let's just, for the sake of argument right now, assume that you want to make use of these materials. You would want to make an amorphous silicon metasurface on a fused silica substrate. So you would start with so this is essentially a glass wafer. You would deposit amorphous silicon, or you can even buy wafers pre-made with amorphous silicon deposited on top. You would spin coat resist, you would expose it, develop it, and now we're going to do something slightly different. So we're going to evaporate aluminum oxide, or I should say, we want to deposit aluminum oxide. And now it starts to matter what method I'm using to deposit this material. So now I'm deliberately choosing a method that's not conformal. So I have these sidewalls of my photoresist are now open, they're exposed. So that means that I can, if I put this into a solvent, I can dissolve the photoresist, and then the aluminum oxide that sits on top of this photoresist, it now magically floats off into the solvent. If I did a good job at sort of making these vertical or even inversely tapered a little bit. So now I have a hard mask sitting on top of my amorphous silicon, and notice, so here now the tone of the process is slightly different. So where I made openings in my photoresist, I now have my hard mask. So this is now where I'm going to make pillars. So this is something kind of important to keep track of when you're designing these processes. And honestly, it's quite easy to make a mistake and end up with pillars where you thought you wouldn't have them. So then you use your favorite anisotropic etch and you define these pillars into the amorphous silicon. You would stop as when you hit your glass substrate. And then if you desire, you remove the aluminum oxide. So the end result might look something like this, where you have these amorphous silicon pillars standing on fused silica. And in the SEM pictures, it's really hard to determine what material is what. And I think in this particular case, I think the aluminum oxide is still remaining on top here. So the etch mask is still remaining here. Okay, so my fourth and final example is going to be using a titanium oxide metasurface on top of aluminum. So this is going to be a reflective metasurface. So you would start with a silicon substrate. So notice how the word silicon doesn't really appear here, but if you can, you work with silicon. And I'll return to that point. So you deposit aluminum onto which you pattern a resist. So you make little holes to define your metasurface. And then you deposit titanium dioxide. And in this particular case, you need to make sure to choose a deposition method that's sort of that's compatible with the feature sizes that you want. So if they're very, very small, you need to choose a very conformal method to kind of completely fill in these structures. Then you would etch the titanium dioxide back to expose the photoresist, which you then dissolve in a solvent in the end. And why I'm showing this example is because this is a very different type of fabrication process where the pillars themselves, so we use etching, but we don't define the metasurface itself using the etch technique. So the pillars, or the metasurface, is here it's completely defined by the lithography and the material deposition itself. The etching is only used to kind of expose the photoresist to kind of release the metasurface from its resist matrix. So this has gotten fairly popular lately to utilize. And the result might look something like this, where you have titanium dioxide pillars that are fairly rectangular, and they sit on a slightly roughened surface of aluminum. Okay, so that's it for my examples. So now I'm going to move into the bit where talk about some of the challenges and some of the considerations that one has to sort of take into account when designing and setting up a process for metasurfaces. So the first thing to note here is that it's kind of implicit in some of the stuff I talked about earlier, but silicon is a very, very common material. It's called Silicon Valley for a reason. It's not called gallium and timonide valley. It's not called silicon nitride valley. It's called Silicon Valley. And it's kind of, it's because silicon is very, very convenient for a whole lot of different reasons. And this is not an exhaustive list. This is just a few of the ones that I jotted down quickly. It's very easy to get a hand on. The cost is fairly low. It handles really, really easily. So if you ever work with silicon, you know that it sits at this sweet spot where you're not constantly afraid of breaking the wafer. If you drop it a little bit, it doesn't necessarily break, but you can break it if you really want to. So if you need to cleave out pieces, that's not big of a deal. And I think importantly for what we're talking about here, it has a very, very well-developed etch chemistry based on SF6 and C4F8, which is typically referred to as the or a Bosch process. So that's what I utilized in the first example where you saw these spindly-looking tall pillars. However, silicon, I mean, if silicon is so good, why don't we always use it? So it does have a few notable drawbacks. For instance, it has a really high or a fairly high refractive index, I should say. So if you now consider having a transmissive metasurface optical element, just by entering and exiting the substrate, you lose about 50% of the light just because of the Fresnel reflection at these interfaces. So if you can tolerate that, great. But if you really want to collect more than 50% of the light, you have to address that somehow. One mitigation strategy, and you might recognize this combination of materials, so you might use amorphous silicon on fused silicon. But here you're still able to use silicon essentially, but you've removed the wafer itself, so you never really enter and exit the silicon wafer. So you can improve on this number here, because the fused silica wafer, I mean, just looking out the window, okay, now they happen to be closed, but if they weren't closed, you know that you don't see a huge reflection of yourself in the window. I think, so there's a way to kind of mitigate this. I think another more of a fundamental issue with using silicon is that it's essentially a piece of rock that we're using, and we know that rocks aren't transparent to visible light. So typically around a micron, it depends on the exact type of silicon that you use, but typically around a micron, if you go to shorter wavelengths, silicon is not transparent. So if you're trying to make a transmissive optic, that's not the greatest material. So there are definitely people who have demonstrated metasurfaces below a micron, but I think you start moving into a regime, especially if you hope to go into sort of blue and even UV wavelengths, now silicon becomes not a great choice. So you then have to move to other materials, such as, and this is a very, very non-exhaustive list of materials, but silicon oxide, silicon nitride, titanium dioxide, diamond, sapphire, etc. But I think my main point is here that as soon as you move away from the sort of silicon paradigm, you are now you're playing a completely different ball game in terms of the fabrication that you try to make, or yeah. So it might require significant process development in order to make that type of etching work for you. So that's not to say that it's not a significant time investment required here, but at least here you have a starting point. You know kind of the gases that you have to use. Here you might have to start. I mean, you have to start by Googling. You have to start maybe asking ChatGPT, about how do I etch this particular material? Okay, so I'm going to switch gear a little bit and talk about, so it was implicit from a lot of the talks this morning that we do care quite a bit about resolution, and I think a very important thing to also talk about then is aspect ratio. So resolution, I think we all have a fairly good understanding, so it describes your ability to print or make small features. Aspect ratio is sort of the height to width ratio of a structure. So if you, let's see here. Okay, so my point here is that resolution and aspect ratio are tightly intertwined in the sense that if you told me, just someone stops me on the street and tells me, hey, I want to make a 20 nanometer feature. My first question back is going to be, okay, how tall is that feature? So you can sort of, it's from this image here, if your feature that you're hoping to make in 20 nanometers wide has to be only 20 nanometers tall as well, your aspect ratio is 1, that's probably fine. If you tell me, well, it needs to be 100 nanometers, now that's a little bit harder, might not be possible, but if you told me, well, it needs to be, my aspect ratio needs to be 500, well, that's probably not going to work. So resolution coupled together with the aspect ratio is a very, very important thing to keep in mind when we're talking about what is possible to achieve when you're trying to make metasurfaces. Okay, I think I moved this onto the, okay, so now we're going to move into a bit where I'm going to describe a couple of the explicit challenges that I do see. I'm not necessarily going to have a lot of the solutions to this, and I think part of this is because Metasurface is such a wide-ranging subject, so it's very hard to come up with like, this is the solution. I think it's going to always be pretty application-dependent and dependent on your exact pattern, etc. So this is a problem for, I would say, most type of etching that you want to do. And that's if you have a situation like this, where your features are, you have a different aspect ratio, and even if the gaps are, so that's actually a very bad example because it's mostly the gaps that are different. So let me do this instead. So if you have a gap that's a few microns wide and you have another gap in your surface that's only 100 nanometers wide, typically the wide gap is going to etch much faster than the small gap, meaning that you will end up with a situation where your metasurface is not uniformly deep. You have sort of patches which are very deeply etched and other patches which are not etched very deeply at all. So that's something that can be very tricky to, so there are definitely ways to kind of get around that and mitigate those effects, but it's sort of always going to be there, so it's hard to completely solve that issue. Another thing that can be very annoying is that you can have a depth-dependent etch profile, so even if you have done a good job for a certain type of etch, so let's say you designed an etch that was supposed to be 10 microns deep. Now you have someone tells you, oh, you can do 10 microns, let's do 100 microns. And you happily, you agree, and you just try to do this for 10 times as long, and now what typically will happen is that your etch profile, instead of being perfectly vertical, will sort of start tapering off, and at some point it cuts off your features and they're not there anymore. So that's something that also is possible to address, but now this is also aspect ratio dependent, so it's hard to completely solve this for the entirety of a metasurface where you're mixing very small and large features and large and small gaps at the same time. Now, if you're hoping to make wafer scale processing of either of small metasurfaces, or if you're talking about making large scale, millimeter or even centimeter size metasurfaces, now non-uniformities in deposition rates and etch rates, so typically a lot of etches, or a lot of chambers, I should say, they etch faster in the center of the chamber on the wafer than they do at the sides, so you then have to keep track of, so even if you're done etching in the center, you might not be done at the edge of your wafer. And now, these are two kind of practical and very hands-on challenges, but I think they're very important to kind of consider at least. And that one is, so this is very annoying if you're a microfabricator, and that's tool performance typically drifts over time. And this can be sort of a slow drift over months or weeks, months, or years. But it can also, unfortunately, be a very sort of rapid onset of something. So someone did something yesterday, and now you return with the expectation that your process that you did a couple of months ago or even the day before is going to behave the same. And then, unfortunately, it doesn't because someone put some other material in the chamber, changing the impedance of the chamber, etc. So I think this is less maybe of a fundamental problem, but it's certainly something that I can see a couple of people nodding in the audience, so I think they've had this happen before. And then I think a big problem as well is if you're hoping to make nanoscale or even micron scale features, particle contamination is definitely something that you need to contend to. And this is, of course, this is heavily, heavily mitigated by working in a clean room environment, but even clean rooms aren't completely clean. So you always have some particle count. And I think even worse, we end up having to handle our materials all of the time. So in sort of big semiconductor fabs, typically people are not really involved at all. So maybe you design the process on a computer and then a robotic arm kind of moves around the wafers. So I think that's probably the only way that you can completely remove particle contamination from manual processing. But I don't think that's feasible in terms of what we're doing here. So in clean room environments, in universities, and even our clean room up at JPL, we are kind of purposely built to allow a lot of flexible processing. So we cross material streams, we cross very different types of processes in all of our chambers, on all of our benches. So I think we will always have to contend with the fact that we have some amount of particle contamination and our tool performances will drift over time. And I think the way to solve or at least mitigate this is we need to move away. So when I started doing my processing many years ago now actually, I had this expectation that if I always did the same time or did the same thing, so I had an etch, I ran it for 5 minutes, I should always expect the same result. That is unfortunately typically not the case. So you need to expect to have maybe, so I thought it was going to etch 5 microns. Well, I etched 5.6 or 4.5 or 4. So I think that we need to, as microprocessors, and even in our designs, we need to expect that things will change, and we need to build in inspection points to kind of handle these annoyances. Okay, so that brings me to my closing thoughts. So to succeed in making optical or metasurfaces in general, I don't think necessarily it needs to be optical, but to succeed in making high precision metasurfaces, we need to have a good understanding of the design tolerances. And I don't think we do this enough in the field. I know I certainly don't. And I think this is a big one where we need to focus not only on the performance of the design as like if it's made perfectly, but also how big of a tolerance do you have in terms of your feature sizes and the etch depths across the metasurface itself. I think we also, this is, in a sense, this is an obvious one. We need a good way of measuring the performance of the fabricated metasurface. And obviously, so let's take metasurface lenses, meta lenses as an example. Obviously, you need to be able to measure the performance. So the focusing efficiency is, let's say, 80%. So that's necessary. But I think here I'm trying to make a point that it would also be nice to have a way of mapping the wafer and checking what is the induced phase and even the amplitude across the surface. So if we can start doing that, I think it's much easier to work backwards and try to address where across this metasurface are the pinch points, if you will, or the problematic areas. Because if you just know that you're focusing at half the performance that you thought, it's not entirely clear how to address that in either design or fabrication. And I think you also need to have a willingness to kind of iterate between design, fabrication, and metrology. And so this is in the ideal world, this is what you would do. You would design something, a metasurface that you would fabricate, and then you measure it, and then if it works, great. Like, you can stop. You don't have to do anything more. But I think we should expect to do something more like this, where you design something that you try to fabricate, and then you realize, well, these feature sizes are not necessarily achievable. So feed that back into the design, redesign it. Okay, you fabricate something, now you measure it. Okay, feed that back into the fabrication. Maybe also you have to feed that back into design and modeling itself. So I think we should, and I'm excited in this workshop to start addressing some of these feedback loops and how one sort of closes this loop in order to have something come out more or less perfectly at the other side of this linear process here. And with that, I'm done, and thank you for listening.